so much for happening to be here. It's a really honor to have you here.
Thank you. Yes. Thank the organizers, first for inviting me here, second for putting up this very interesting meeting. And we need more of this, where, okay, pure mathematics come head to head with, even with the experiment. And they were in the list of the invited people, two experimentalists now, but I think, so definitely we need more of these meetings and make, like my students say always, make mathematics consequential. They say, well, we learn some unconsequential mathematics. There is nothing like that. Every piece of mathematics consequential. You just don't know. So what I will discuss today is actually a program invented by Jean Belisard. It happens to be in the context of twisted bilayers, because this now is a hot topic in condensed matter, but what I will try to emphasize is that the machinery works same way in so many different ways, and everything comes from what Jean Belisard told us in 1985, and quite interesting, we are still learning what he was trying to tell us back then. And so my plan, oh maybe
I know, it's just we need to do something with. Oh, but try again.
So my plan is to start with some examples and to show you some numerical results. Why? Because if I start the other way with the mathematics and then I show you some examples, things kind of become trivial. So I want to show you when you start from zero and somebody presents to you this, you feel like, well, what there is nothing you can do. Maybe you just go with brute computer calculations on it, or it so happened that I was contacted by Mateus and Massimo. They are at University of Colorado in aerospace department. They are working on wave engineering and designing interesting metamaterials for various purposes. And I had a very different impression about the engineers, but engineers in academia, they are really academic. I thought will be going and solve different engineering challenges, but they were really interested in this stuff, K-theory. So here, that's why okay, I'll be talking about a system of spring and balls. This will be phonons, if you like. So this will be the atoms interacting, and we will be looking at the vibrations rather than electrons, but we can also look at, think of this as okay, a 2D electronic material sitting on a substrate, but the electronic degrees on this substrate do not hybridize with what's below. So this supplies potential, and it modulates the interaction or the hopping terms between the sides, but other than that, it's inert. So then this periodic potential, if it's a line, we have the simplest system ever, but then if we twist the potential layer, then the potential is no longer aligned with the lattice, and we start to see patterns like this. Now, for some very special thetas, the system can be periodic, but typically the unit cell is really large, so it's almost useless for calculations, and then for generic values, it's non-periodic. So there is non-periodicity, and well, if here, well, if in that instead of this yellow, I would have put dots. When I started some time ago, I tried to label these points in some way. I thought I can label them by some abelian group ZD, and what will happen if these are incommensurate, you can label this as 0, 0, 1, 1, 0, 1, 0. But then if you try to put integer labels on this, you will see that soon enough, the labels that you put, they are so far away from each other. So when you're over here, this will be labeled by 100 and this one by 10, something like that. So there is no way to label these points by an abelian group. So that is gone. So you have to do something bigger. Now here is the Lagrangian for that system, a kinetic potential, kinetic energy, the potential, which is twisted, and a coupling. In the regime of small oscillations, we have an equation, which is an eigenvalue problem for the resonant frequencies. And I will not, my talk will not be at all about what this term does or what that term does. In fact, all the statements will apply to this general hopping Hamiltonian, where what we have, this M and N label the masses, so those we can still label by an M and an N, by Z2, but then the coefficients, the hopping coefficients are fully determined by the whole pattern. What is that? Is the first layer and the second layer. And here are some choices for which I will show some numerical. So here is, if you, I had here some parameters, so A1 and A2 and beta. Yes.
You allow damping in the equation?
So no damping here. So all these eigenvalues will be real and nice. And so here is that beta A1 and A2. So this is two square lattices, and they are twisted by an angle theta, and we will vary this theta from 0 to pi. If I plot the eigenvalues, you see this not so nice picture. But the minute you pass to the density of states, then you see that although here are eigenvalues in these regions, their density is so small that in fact they are real spectral gaps. If I will do this picture in the infinite size limit, then this will be really empty regions. Now, if you look at such a spectrum, it reminds you of the energy spectrum of electrons in a magnetic field. So that's one connection. And in this graph, I am plotting the integrated density of states as a function of this angle theta. Well, the formula is here, but what it means, you start with a certain size. There are a finite number of atoms in the system. You pick a theta and you count how many eigenvalues, rather on this graph, you have up to a value omega squared. And you take that number and you divide by the total number of atoms in the system. You get a number, and this is what is plotted here. So let's say on this axis I have this number, on this axis I have theta, and the color is actually the value of energy. And you see these all kinds of lines. They are called 1-year lines, but what are they? So when you see this abrupt change of colors, what it means when you look, if this was a real 3D plot, well, it means the graph shoots exactly at you out of page. So here the graph comes and here it jumps. That's what this color. Well, where it can jump? Well, I can tell you that this jump here happened exactly here. Why? Because as you vary the value of energy, the integrated density of state stays the same. You don't cross any eigenvalue. So in each of these gaps, the graph shoots at you, and therefore you will see a abrupt change of color. So each lines here, in fact, allows you to compute what is the value of the integrated of states inside the gaps. So this line here corresponds to this gap. This line here corresponds to that gap. We have many lines here which corresponds to these lines, and so there are so many of them, and we just try different lattices. In fact, Mateusz tried different lattices and found the same Hofstadter kind of spectrum, and then when plotted the integrated density of states, you see these lines. So Mateusz didn't tell me what are the details of his Hamiltonian. He didn't tell me anything about these parameters or his choices. What I said, why don't you fit all this with this expression? And what's amazing is that every single line that you see in these three graphs can be fitted with this expression where these ends are integer numbers. And well, if you don't know where this one comes from, it's almost like magic. It's how can you say something without even knowing what the Hamiltonian is? And I put this slide here that the mind setting is actually really important in this endeavor, much more important than details or anything. Well, we know winding numbers, so if it is to classify these loops on a plane with two punctures, then we know what's going to be. Now, of course, when you look at this picture, you say, the loop is the main actor, but in fact, the main actor in this picture is not the loop, but the space. If you know the space, you know what you will find here. You will only find loops which go n times around this one and m times around that one. There is nothing else. And it's the same here. If you know where these Hamiltonians land, what is the topological space for that, then you actually know what you will expect. What we are IDS is the simplest topological invariant you can associate to an algebra. So an algebra with the trace. So that's why I was able to predict all this before he told me what is the Hamiltonian. So let's and it's very interesting. So that's the main actor in this picture is the loop. Now, usually condensed matter physicists identify one number, most favorite one, the Chern number. But in fact, in this case, you need two numbers, and if you have more punctures, you have many numbers. If you just find one number, then you will be talking about an obstruction. But if you find all the numbers, then you will be talking about the complete topological invariant. And we are, I am after this, so I don't want to just pick up some obstruction. I really want to know what this space can offer to us. And very important is that this complete topological invariant, which is the pi one of the puncture space accepts an algebraic structure. So even that this loop is very complicated here, it's just a composition of n times one single loop which goes this way and n times a loop that goes in there. So by just specifying the two generators, you know what this space has to offer, and it's time to move on. That's without leaving anything behind. So, can we do the same for this structure? So, what kind of topological phases we have here, and enumerate all of them without leaving any of them behind. So, what else? For experiment, it's very important actually to communicate what is space where the Hamiltonian land is. Why? Because, for example, I put two pins on a surface. I want two loops, one red and one, and I asked my daughter, well, can you try to deform the red one into the blue one? Well, I knew she could not, but guess what? She pulled them up, and she said, look, I didn't do it. Was my mistake, because I didn't tell her that you need to stay in plane. You are not allowed to pull it up. So any prediction actually holds as long as you don't escape this space. And that space and what you need to do to stay inside that space needs to be communicated to the experimentalist extremely clear. Why? Because if you go in the lab, everything that can go wrong, it will go wrong. And they will say, well, you know, it's not like you say. And then you go, oh, I forgot to tell you that you are not allowed to do this. So it's very interesting, because at the end, we will communicate this by a sister algebra, which is very, that's why one way one will learn mathematics, because with a few words you communicate huge amounts of information. And I always say, with drinking morning coffee and talking, you can communicate huge amounts of information by just mentioning names and of course, if you have the background in the context of the discussion. So now I'm coming to this fundamental observation by Chern. So we are starting with this ugly Hamiltonian. We have this hopping Hamiltonian, and these coefficients in front, they are determined by this lattice itself. This lattice, so this is it's a pattern. We should see it as a point in a topological space, exactly like we see a point in 3D. And in fact, we can even put coordinate system if we like, if we want. What else? Well, they should depend continuously on the deformation of this pattern as I twist or if I squeeze. They should have a finite coupling range, or at least should be approximated by finite coupling range in a sense that needs to make precise. And now the underlying physics needs to be Galilean invariant. And here always got in a lot of trouble with this. What it means. So these are two resonators who are part of the lattice, and these two fellows observe this resonator, so they have moving parts from their frame, which is rigidly attached. What they are observing? Well, they are really hitting the resonator and they are observing the dynamics. They are hitting again, observing the dynamics. That's all they do, these fellows. And it is that kind of process that they use to actually map these coefficients. Now, if you take the whole material and you move it like this, they stay in there, so they see the resonator from the same moving coframe. They will have no idea that you actually did that. Why? Because the physics at low energies is Galilean invariant. So that's mathematically what it says here. Now here I use translation and rotation. So it's this will happen for the full Euclidean group, but in this talk, because we only have points, we only use translation. So if I translate the pattern and I relabel the points, I should actually, these values should map the same coefficients. And with this kind of empirical input, Chern told us like that. If you fix the pattern and assume that you have the means to unrestrictedly change the internal structures of the resonator so that you change this, but you at every point you satisfy these constraints, then any Hamiltonian can be generated from the left regular representation of a computable sister algebra. Sister algebra can be computed, and I put here this term separable, which is the most important of all, because then the K-theory is countable, so we can enumerate the topological phases, as opposed when this one is not separable, then you cannot enumerate them. It's there is nothing there. I mean, the invariants that you can cope, they take continuous values, and then you don't have a sensitive classification. So that's our challenge always. To even if we start from von Neumann algebra, we need to find the sister algebra behind it, and it needs to be separable. This sister algebra can be explained very easily. It's a groupoid sister algebra, and it comes simply because these patterns are closed patterns in the Euclidean group at the end. But I will show you a way to calculate this algebra, which will be very familiar and very elementary at the end. So too fast, but maybe after I do this calculation, I will show on the blackboard how for any pattern of points to arrange this, you can actually derive a separable sister algebra, and that will be the start of the calculation. So let's see. Since we have this this equivariance under these transformations, we actually can eliminate one of these indices. And if I call this one Q, we will see that the Hamiltonian or the dynamical matrix can be written in this way. So what we have here, we have the shift operators, which simply shifts the index, and then inside this parenthesis is a diagonal operator. So the conclusion will be that these operators always land in the algebra generated by two shift operators and diagonal hints commuting operators of this form. Moreover, I can calculate what commutation with the shift operator will do on this expression, and you will find it here that if you take take the shift operator from the right and bring it to the left, then that's the same as computing composing this F with a shift map on the patterns. So not only we found how this algebra is the generators, but also we found the commuting relations, and any other commuting relation, any other S1 commutes with S2, and of course I already said that this one commutes. So now the plan really is like this. So this guy here form a commutative algebra. It should be isomorphic with the C-star algebra of continuous functions over some space, and we need to calculate that space. In physics literature, this space is really the Phasor space. So, was it the meeting was on quasi-crystals, and the Phasor is the star of the show, and somebody was asking how will we explain to mathematicians what the Phasor is. And it was funny because they didn't know that we had actually the notion of the Phasor for any pattern, not for very specific patterns of quasi-crystals. So this is the Phasor space, and it needs to be computed. In fact, it's quite easy. I'll put the resonator layer. So here are the active degrees of freedom. Here is the potential layer. And okay, if we just put them randomly on top, let's see, can we make a one-to-one correspondence between this pattern and something that we know very well, like the points of a torus? And the answer is yes, because here it is. This fellow always stays at one of these nodes. He looks up, and he sees this projection, his projection inside one of these cells. It will always be inside of one cell. If he knows its position inside this cell, he can put down the cell itself, and from here on, he can tile the whole plane. So it means, really, this pattern is in one-to-one relation with a point on that torus. And if it lands here, or it lands here, it's the same pattern to the eye. So it's not, these sides should be, they are one, so we make them, we wrap that into a torus. Of course, this fellow needs to know what is the units, what are these things, and how is the twist angle, and that's an information available to our fellow. So really the Phasor space for this pattern is the torus, and if this fellow jumps, what will happen, it will be a shift on the torus, which really goes by that rule. And it's we need to know not only the space, but also how the shift acts, because we, as you can see in this formula, P is always active to the shift. So now I can finalize the calculation. We will be talking about functions of patterns, but then they become functions on the torus. Discrete Fourier transform tells us that these are all generated by two very simple functions. So this whole algebra that I mentioned at this point is generated by a T1 and a T2 corresponding to an F, which when evaluated on the point of the torus, returns that value. This together with the commutation relations, which were here, you can calculate, and you find out that at the end of the day, any such ugly Hamiltonian lands in this algebra. So it's algebra generated by shift 1, shift 2, and by T1, T2. And what is that? It has these commutation relations where phi is this matrix. So any Hamiltonian which obeys those empirical constraints come from this non-commutative torus with this modify or twist entries, and here I put a multiplication which takes care of how we populate the sides with orbitals. So if we have n degrees of freedom per side, here will be n by n matrices. So that's where this Hamiltonian come from, and knowledge on this algebra enable me to give the experimentalists this fitting function. So to remember, I communicated this and that. This one is known for that algebra. So I know that. So I have slides in which I will show how it comes about. Okay, so it's a happy case where Jean Belisard program can be carried explicitly in a very elementary way. What do I want? I want to make this mathematics consequential, so I really want to go into a lab and tell the experimentalists how to observe and confirm this. So this was very elementary mathematics, but when you see it in the lab, it feels like the proof is not on the paper, but it's rather in the lab. It's that's the ultimate proof. Well, with this, within this program, yeah, this was an elementary exercise. Yet, out of it, we squeezed about 10 papers along the same thing, and it was a lot of fun. In the meantime, the engineer starts to be very comfortable with words like K-theory, pairing, sister algebras. Yes. Okay. Now, where is this sister algebra? Well, this is, you would say, this is just an algebra, but since we want this to be a topological space, at the end you have to put a topology on the space, and C-star closure of this algebra is how that topology will come, and it's something standard, and I don't have to explain what once I figure out the relations, generators and relations. Okay, since I might go fast, I'll say.
Okay, sorry, can I ask?
Yes.
So I'm the experimentalist who asked the naive questions. So
Yes.
I'm sorry. So all these conclusions are invariant under the type of lattice that you have. Like, for example, is it valid for square lattice, hexagonal lattices?
Oh, that's right. The details are different, so I need to. As you can see, why you need to put here is A1, A2, and the beta. And here, well, here we will be assuming that it's 1 degree of freedom per unit cell. So if you have more, then you'll have to take that into account. But the conclusion will be the same. So I'm very glad you interrupt, because well, we went to fabricate this, and what we did was we took a system, a lattice of pins. So we put pin in a regular lattice, and then we know that well, the resonant frequency of this guy sort of depends on its length. So I want to vary the resonant, on-site resonant frequencies. So I just chop them according to a rule which was that. So I have a length which depends on theta. So if you look at this, it will look like a forest of pins which were cut at different lengths. And by doing so, it's really I modulated the on-site resonant frequency of the resonators, which is exactly like putting a potential, local potential. But we ran into some problems. These pins have 2 degrees of freedom. They go left. So when you map such a spectrum, then you'll have this and another one on top of each other. And since these gaps can be quite small, 2 degrees of freedom gave us overlapping bands over gaps, so they were really tiny. At the end of the day, we really wanted something which has only 1 degree of freedom, and here is where I thought that the engineers would go and solve that one, but they say no, it's good enough. Either we leave it at this theoretical level. So we have not implemented this system, but a lot of other aperiodic modulations where we were able to make predictions with the, for example, incommensurate lattices. We were able to, for the first time, to do a dynamical Towless pump of sound from one end to the other. It was predicted and thought it was, but the experiment actually it's quite demanding because it's you have to reconfigure your system. You have to reconfigure it fast so that the signal which you loaded on this end, when it gets to here, it doesn't die out because of the dissipation. And these mechanical resonators or acoustic resonators, they have maybe a Q factor of 20, 30. So you really need to reconfigure fast, and we had to generate more options so that our system can be reconfigured fast. And the easiest one was to have resonators like this, a resonator like that. They were coupled to a thin layer, and this being like so, you can push them like that. And when you push them like that, you vary the phase-on. And in this case, the phase-on lives on a pretzel. So as you push this one, then you modify the pretzel, and you get an extra dimension, and that is where the Chern number shows up, and all this pumping, topological pumping comes in. I suppose in another experiment we had screws here, and we were able to modify the length, but then you will need somehow to do it for 100 of resonators in sync, so you will have a whole electronics here to rotate these springs, and that was not possible. So even though it was a variation on the same theme, giving the experimentalist options was of good value here. Now,
Emil, I have a
yeah.
question. So these non-commutative torus that you have there, we know that there are 2 different ones. The one with the rational exponent, one irrational.
Irrational.
And since you're saying that you're taking this generically, I suppose these are theta irrational.
That's right.
But then you cannot do that computation. Any number in the computer
So
is
any
rational.
number, yeah.
So I suppose this is just experimental, real things. You put 2 layers randomly, and then.
So this was a numerics. Well, in this case, there's something periodic. So
like
what
a rational
happens? This was a very large supercell, and this is why the points that you see here are the dangling bonds around the edges of the supercell. So when you plot it like this, of course, and if you plot it like this, they will not go away as you take the lattice larger and larger. But you plot it this way, then you have this nice phenomenon that the volume goes with L to the third, while L squared, while the boundary goes to the L. So the density of these fellows is much smaller than the density of those guys. As you increase the size, the picture clears up. That's because we are talking about amenable groups. So when we went to hyperbolic geometry, that is no longer the case, and in fact that's where we found this work by Luke. It's in chapter 13 of his book on the proximants of the L2 invariants. And when you apply that machinery, the whole numerics clear up.
So just to follow that question, there should be an infinite number of these color changing transitions then, right? In the truly aperiodic one.
In the truly, that's right.
And can you characterize all of them with this fit function?
So very good question. So we will you will not be able to see the very small ones, but there is enough here to test what you are saying. So in here, if you find any, for example, there is a tiny one here and a tiny one here. If you cannot fit this one with the curve that I show, it means I had not predicted the algebra correctly. But that was my task for Mateusz to look for each feature here and see if he can fit it with the
So there's an infinite number of fit coefficients that
fit.
describe.
That's right. And
but the functional form is constrained by the algebra.
that's right. And it's a very interesting thing that, for example, if you have something like this, n plus theta, if you give large values of n, large values of n but negative, you can land again in the interval 0, 1, and you can fit this interval densely. So if you see a gap in your spectrum, then which one will you pick? Because you have. So it's very important that we actually vary this data, because then we have not one value, but we have a whole curve, and then we can fit the whole curve rather than one value. So this is what, when we wrote the paper, of course we hope for a top journal, and the reviewer didn't understand that look, it's like magic. It's everything in this picture you can, and he thought we are talking about the 4-second Chern number, and but that was really, once you have the algebra, that comes for free. It's there.
Can I ask you a question? So
Yes.
the only thing on this is this algebra is for a fixed data and they're all the same, or are you having like a
Yeah,
solid
so
function?
this will be for a fixed data.
Okay.
Why? Because this A here are these
Yeah,
expressions. So now you can recognize where these sign ratios of signs come from. Okay, so what I will communicate. So keep the twist angle and the geometry of the two-layer fixed, but you are free to deform the twisted background. In the process, you change the on-site frequencies, but also how the resonators couple to each other. So think of these resonators coupling with magnets, and then you put a magnetic or a ferromagnetic layer, magnet, 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 and if you put something in between, you immediately alter how they are coupled, so that, and then you are free to deform the internal structures. You can turn on and off degrees of freedom. You can also enforce fundamental symmetries, time reversal, chiral and particle Hall. And then this is what will be the predictions, that I know precisely when two gap Hamiltonian can be continuously deformed one into another, when, if and only if their classes coincide with the appropriate K-theory of this three-star algebra that we just computed it, there is a precise set of response functions that remain quantized. What are they? They are generated by pairing with cyclic homology, and this K-theory that I mentioned. So in these conditions, this twisted system cannot offer anything else than what is in here. So if you're looking for something exotic, I can guarantee you that it will be in here. Well, it's the same story when topological insulated field started. People were finding lattices with Chern number 6, and the lattice was so nicely engineered, but at the end, that is, you can be sure that you can deform the coupling constants so that that is just uncoupled 6 layers of Haldane model. So there is nothing in 2 dimension, there is nothing else than Haldane model. Everything else can be deformed eventually in the Haldane model. So that's the same message here. There are only a finite number of model Hamiltonians, and everything else is either layering and or it can be continuously deformed. And all that it comes once you calculate this topological space of the Hamiltonians, and it's nothing more different than the loop space loop that I mentioned before. Once you know the space, you know what it can offer. So quickly, of course, when we put magnetic fields, we are wondering how we calculate numerical topological invariance. But in this algebraic context, it's quite easy. So an element is really of this form. So we have these U generators, we have coefficients, which are matrices, not numbers. And then you have d derivations, if we are in not with 4 torus, but d torus. And then we have an integration. And like you will write the Chern number on a smooth torus, you will write it here in this way. So it so happened for non-commutative torus that this cyclic homology is generated by cycles of this form, and then since the number of these cycles, independent cycles, equals the dimension of your group, then you know that once you know this number of invariants, you immediately locate your Hamiltonian in its K-theory class, and every other numerical invariant will be actually linearly dependent on these ones. So what you see here is nothing but the top Chern number and the weak Chern numbers, and there is nothing else for non-commutative torus. Now that I was saying, there is almost every question that one might have about this algebra is no. Here is the values of when you compute the weak Chern numbers corresponding to a set of directions. So so this J is a set of directions, and this is let's say one of these the generator of the K-theory, but one should think of it as the these fundamental models, which once you found them, everything else is layering and of those. So we have a prediction here how it goes, and out of this prediction we have a few corollaries. The integrated density of states, it's really the lowest of the lowest Chern numbers. So it's just the trace per volume of the gap projection. It's really the number of eigenvalues below the gap divided by the size of the system. And using this prediction, we have a formula, and I calculated these Pfaffians because I know what the matrix F is, and this is how I already said this prediction came about. But then there is also a generalized Streda formula. So the Streda formula, we say that if you differentiate the density of electrons, I guess, by the magnetic field, you get a Chern number. But in fact, if you take any weak Chern number and you differentiate with the flux through a phase set, which is not engaged by that weak Chern number, you get a higher level, two higher level Chern number like here. And this can be used to find a very interesting effect of this twisted bilayer.
How did you pump up 2 degrees of freedom just by 1 in this, in what you just said? You just said that if you take it, you went
by 2.
by 2, yeah, but
so
you only have 1.
So I put here, so this set of indices enhanced by 2, so you go from.
Same thing in geometrically, you have some sort of geometrical information of degree 10, and then you pump it to degree 12. So how? So you have to do 2 directions to pump it.
So as you can see here, I have to take the differential with respect to the
to some 2 elements. Yeah, I see. There are 2 elements.
With respect to the twist.
Exactly. So it's 2 elements already. So the non-commutator of 2 elements.
Yes.
I see. Oh, nice.
So the weak Chern numbers don't take integer values. Only the top Chern number takes integer values, and then you have these differentials which pumps you to the next Chern. Well, you can imagine that through this fitting, we were able to calculate what are the complete set of topological invariants which are listed here for many of these gaps in the systems, and were listed in this table. So it is computationally effective, but let's look for if mathematics can tell us something new. And now in condensed matter, of course, every day we find in the literature one more and new physics about bilayers. If we look at these layers, what can we do? Well, we can slide them like this or like that, so we can change the value of this zeta, or we can twist. None of these actually were ever proved in a lab, but here is what they will give us. This is edge states, so it's a system with a K boundary, and one of these xi's are varied. So I am, if I put a boundary here, so I cut in along here, this will be a 1 boundary because it cuts the direction 1, and I am holding this one still, and I am sliding the top one this way. So when you do that, this kind of network comes out, and how will you characterize these ones? Should be, there is a bulk boundary correspondence, they should be related to the bulk topological invariants. Different graphs correspond to different cutting directions, and here you see which parameter was varied. And yes, you can, there is a very, for the non-commutative 4 torus or any dimension, there is a very clear full boundary correspondence. And in this context, it says that the effective number of bands, what it means, if you see a band going this way, you count it with a plus, a band going this way, you count it with a minus. When it intersects a fixed horizontal line, that's this number here. K is indicates how the boundary was cut. I indicates which of the sides were varied. And if you divide by this square root of the dimension of the lattice, you should find that is equal to the appropriate Chern number. And since we had a prediction for this Chern number, here is what we had to check. And indeed, each of these plots, these numbers were already mapped in those tables that I showed. This one is the top, the second Chern number, and everything checks for the edge states in here. Well, in this plot, for example, you see bands going up and down, but these bands together with this one are 4 bands on the left side of the boundary. These other ones are 4 edge states on the right side of the boundary, and you can check that these two are at the opposite boundary. So overall, you will always have an equal number of right moving bands, left moving bands. So it checks, and what this means? It means, physically, it means that S, here is the boundary, it means that as we slide this one up, electrons from the valence states will be pumped up into the conduction band. And it will be happen quantized in that way per length. So each unit length will pump up a very specific number of electrons. Now, this one, it's never semi-infinite. You cut an edge here, you also have to cut an edge here. So what will happen? These electrons which were pumped to the conduction band, in fact, will be pumped back on the other side into the valence bands. At the end, what happens here, by moving this one, you set a current which goes this way. So all these conduction electrons, they move from this side to that side. So it means there is a Hall effect when you slide along C1 direction, but then what happens if you slide and then you vibrate this angle theta? So the top layer you slide and the lower layer you well, in that case, there is a Hall effect. It involves this weak Chern number of direction 1 and 3. 3 because psi 1 is, in terms of direction, is indexed by 3. So this will be this current which I discussed that flows to the sample. As you vary this one with the constant speed, and this one is an average over the cycle. So this fellow will cycle again and again from 0 to 2 pi. So it's an average over the cycle and average over length. Okay, we have this variation of theta, so I'll do an expansion, assuming that it's a small variation. When I do an expansion, I see this derivative of the Chern number with respect to the phi entries. And here it is where this thing will prove useful. Why? Because then it tells me that out of all this derivation, only the indices ij, which do not overlap with 1, 3 remains, well, they are 2, 4, but this one then becomes the top Chern number. So it means, if you read here, you will see a oscillating current, and the magnitude of that oscillation is proportional with the second Chern number. Will certainly not be an easy experiment, but that's something that exists in a bilayer. So this is my last slide, and I'm coming back to the beginning of my talk, saying that all these details that you've seen can be repeated again in so many different contexts once you calculate the C-star algebra, and that was really what Jean Pélissard was trying to tell us in 1985. So be aware that behind an arrangement of atoms or an arrangement of resonators, there is a C-star algebra. Once you find it, you can put it in the first page of Alain Cohn of non-commutative geometry and push the whole machinery through. And then explicit things like these ones certainly will pop up. Thank you.